Okay, now we are going to talk about Clarke and Planck's transformation. So, right now, the issue we have is that we have three phasors. So, we have phasor A, here B, and C. This is 120 degrees apart each one of each one. Okay, so what Clarke transformation does is move this of three reference of this three phasor reference frame into a two phasor reference frame. So we have here the alpha axis and the beta axis. So what we want to do is move from this three to this two. So if we look, we just need to make the projections of each one of these phasors, of each one of these frames into beta and alpha. So if we want to represent this into the alpha reference frame, we know that the phasor A is already in the same frame that alpha, so this is just gonna be the phasor A. And now we have this phasor B, and we want to move it projected into alpha, so we multiply by cos of 120. And similarly, this phasor C, we multiply it by cos of 240 to have it projected in alpha. We can do the same for beta, and we know that the phasor A projected in beta is going to be the phasor A times sines of 90 of 0, I'm sorry, because A is 0 degrees with respect to beta, plus the phasor B sine of 120 plus phasor C times sine of 240. Okay, so we simplify this a little bit. It's gonna be phasor A times phasor B cos of 120, and that's just minus 1/2 phasor B minus 1/2 and cos of 240 phasor C. Now for phasor beta, you're gonna have this is just 0. Sine of 120 is square root 3 over 2 phasor B plus, well, minus the square root 3 over 2 the sine 40 of the phasor C. Now this is a transformation, so it is better to write it in terms of a matrix. So we have phasor alpha, phasor beta, and we're gonna have here, this is 1 minus 1/2 minus 1/2 0 square root 3 over 2 minus square root 3 over 2, and this multiplies by our components. So this is how we go from a three-phase to a two-phase, to a two phases reference frame. And now if we can go back the other way around, So we have the phase, we have alpha and beta. We want to get FA, FB, and FC. We just need to transpose this matrix. So it's going to be 1 minus 1 half minus 1 half 0 square root 3 over 2 minus square root 3 over 2 times our components, and all of this multiplied by 2/3. Okay, so this is the Clarke transformation. Now from this we are going to have a reference frame that is just two phasors like this, but this reference frame is stationary, so this is no more. There is no angular velocity here. So if we had a control system and we were measuring our signals, we will still be getting in AC, something like this. And in terms of control, this is hard. So there is another transformation called uh, Planck's transform. What it is doing is just having a reference frame of dq, but this one is moving in an angular velocity. So what we see is that if we move this reference frame in the same velocity of our phasors, then we're gonna have that our control system, when it's measuring, is gonna sit in DC. So this is what we want. So how do we go from here to here? It's gonna be pretty similar to what we did before. So let's start by having here the reference frame of alpha beta. Okay, and now here I'm gonna add, on top of this one, I'm gonna add our other reference frame dq. Okay, and I'm gonna have a random phasor that I'm just gonna call B. So here we have our phasor B, and we can represent this phasor B in terms of uh, alpha beta. So we know that a phasor, for example in alpha beta, is just going to be the magnitude, and we know it's going to be the magnitude of the phasor and an angle. And what angle this phasor has in terms of alpha beta, it's going to be this one. We call this theta. And we can do exactly the same thing for this phasor represented in dq reference frame. dq. So we are gonna have our magnitude, okay? And here, well, what is the angle in respect with this reference frame? It's gonna be this one. It's gonna be psi. Let's call it psi. Okay. So these two are the same phasor, just represented in different reference frames. And if we look at them, the only thing that is changing is the angle. So we know that here we have an angle between the two reference frames. This angle between the two reference frames, I'm gonna call 5, is what we can use to connect these two references. So we know that 5 is gonna be equals to this angle theta, the big one, that is in the alpha beta reference frame, minus the small angle psi that is in the dq reference frame. So we know this is the angle phi. That is the angle between both of them. So now we can say that, for example, psi is equals to theta minus 5. So we could represent the phasor again, b dq is going to be equals to the magnitude. And what is 5? 5 is just theta minus an angle. Theta minus an angle. So what we can separate this. We can say that the phasor in dq reference frame is equals to the magnitude times the angle theta times 1 uh, minus 5, or the angle 5. So if we look at this is just our phasor in our alpha beta reference frame. So phasor in dq is equal to phasor in an alpha beta reference frame, this, minus an angle 5. And we know that 5 is the angle between the two reference frames. So if we want to go from dq to alpha beta, we subtract an angle. And if we want to go from alpha beta to dq, no, if we want to go from alpha beta to dq, we subtract an angle. And if we want to go from dq to alpha beta, we add an angle. Now another way that we can represent this is in a Cartesian form. So the component in alpha and the component in beta is going to be equals to, if we remember uh, the identities, is just going to be here the component in D plus the component in Q, and this we can represent to the exponent of J5. So this is how we can do the Planck's transformation. And the reason is so we can get a DC signal for our control system. Hope this helped. That is it.